How's it going, guys? Today in this video, we're going to be going over Module 9.3, Day 1. In this section, or in this module, we're going to be talking about more complex versions of rational functions. So in 9.2, we looked at rational functions in the form of a first-degree polynomial over another first-degree polynomial, or really just one all over a first-degree polynomial, one of the two. But in this section, we're going to be looking at a more complex version of those. So we're going to be seeing polynomials in different degrees other than just one. So in the first three graphs that we see here, we can actually see these are kind of examples actually of rational functions in the form of a polynomial over another polynomial, just different versions of them. And the last two, in the second two, we can see that we have something called a discontinuity, or really just breaks in the graph. Right in the middle one, in the middle graph, we see we have three little branches of the same graph, but they're divided because they're discontinued on the two vertical asymptotes at x equals -2 and at x equals 2. And the third one, we only have one break, and we see we have we have two different branches of the graph on both sides of the asymptote of x equals -1. Okay, we're not going to spend too much time on that. I don't think it feeds into this lesson too much. So we're going to keep on going, and we're going to look at the next three graphs we have here. So in the first graph, we have the function y equals x minus 2 times x plus 1 all over x minus 2. And when we're actually looking at this graph, or not the graph, but really the function itself, we see we have two factors that are the same, the top and the bottom. Right, x minus 2 is in the numerator and in the denominator, so that means you can actually cancel them out. I don't know why you did that. But we can cancel that factor out in the top and in the bottom. So if we cancel both of those out, what we're left with is y equals x plus 1. Okay? And anytime you cancel out a factor in the numerator and in the denominator, you have to realize that that's going to be a whole. Anytime you cancel out a factor, that's going to be the x value of your whole. So we cancel out x minus 2. You cancel out the factor of x minus 2 anyway. And what we're going to do is set that equal to 0 and solve for x. And when we do, we get that x equals 2. And that's going to be the x value of our whole. Okay? And we have a whole because we see on the graph that actually discontinuous at that point. Since if you plug in a 2 or the x value of your whole into the original function, we're going to get 0 over 0. And that doesn't really work out. So that's why we have a whole there. All right? Or just, if you want to think about it, in simple terms, if you ever cancel out a factor from the top and the bottom, you're going to have a whole when that factor equals 0. Okay? So we have a whole when x equals 2. And what we're going to do with that x equals 2 is plug it into our new simplified equation. Okay, so we have y equals x plus 1. We're going to take that x value of 2 and put it into that function. And we get y equals 2 plus 1, or just 3. And that's going to be the y value of your whole. And we can see that this whole is at 2, 3. So that's how you find the ordered pair, of the whole. You're gonna anytime you cancel a factor out from the numerator and the denominator, you're gonna have a whole. All right. And for your vertical asymptote, you always find vertical asymptotes from your most simplified version of the equation. So our most simplified version of the equation is y equals x plus 1. And vertical asymptotes only happen when the denominator equals 0. But with y equals x plus 1, we don't actually have a denominator. And if we don't have a denominator, we cannot have a vertical asymptote. And we can see on the graph as well that we don't have a vertical asymptote on this graph, so we don't have any vertical asymptotes. Okay? Now for the second graph, the middle one, we have x minus 2 all over x minus 2 times x minus 1. And we can see very similar to the first one, we have the same factor on the top and the bottom, that x minus 2, and that means we can cancel it out from the top and the bottom. And if we cancel those factors out, what we're left with is 1 all over x minus 1. And like I said before, anytime you cancel out a factor from the top and the bottom, you have to consider the whole. There's going to be a whole if you cancel out factors, and when that factor equals 0 is where the x value of that whole is going to be. So we cancel out x minus 2 from the top and bottom. We set x minus 2 equal to 0. We get that x equals 2, and that's going to be the x value of your whole. And what we do with that x value of the whole is we're going to take it and plug it into our new simplified version of the equation. So we have this y equals 1 over x minus 1. That's our simplified version of this equation. We're going to take that 2 and plug it into that y equals 1 over x minus 1. And when you do, you get y equals 1 all over 2 minus 1, or just y equals 1, right? 2 minus 1 is 1, and 1 all over 1 is 1. There's not a lot of room here, so sorry if it's a little cramped. We probably should have put some more room in there. Okay? Anyway, that's how we get our whole. Anytime you cancel a factor off from the top and the bottom, that factor gives you your x value of the whole. You take that x value, you plug it into your simplified version of the equation. In this case, y equals 1 all over x minus 1. That gives you your y value of the whole. You take that x, plug it into the simplified version, you get your y value of your whole. And now for our vertical asymptote, we're going to look at our simplified version of the equation, y equals 1 over x minus 1. And the vertical asymptote will happen when the denominator equals 0. So our denominator in this case is x minus 1. And that's when that equals 0, x equals 1. So that means our vertical asymptote is x equals 1. And if we look at the graph itself, hopefully you didn't write all over it like I did, but if you see in your notes, our vertical asymptote does happen at x equals 1, and our whole happens at 2, 1. Okay? Now for our last graph that we have here, we have x plus 1 all over x minus 1 and x plus 2. We don't have any factors that are the same in the top and in the bottom, so we cannot cancel anything out. So if we can't cancel any factors out anywhere from the top or bottom, that means we have no holes. There are none. And we can see on the graph as well that we don't have any holes, we don't have any discontinuities by a hole. We only have discontinuities by vertical asymptotes. And our vertical asymptotes are going to happen when the denominator equals 0. And our denominator is x minus 1 times x plus 2. That's what our denominator is. So when this is going to equal 0 when either one of these two factors equals 0. Or in other words, when x equals 1 or when x equals negative 2. So our vertical asymptotes are x equals 1 and x equals negative 2. Okay? So vertical asymptotes are going to be what sets the denominator equal to 0 in your most simplified version of the equation. Your holes happen anytime you cancel out a factor from the top and the bottom. Okay? And now we're going to go ahead and just kind of summarize everything we just learned. So in conclusion, holes occur if factors of the numerator and denominator cancel out. Vertical asymptotes occur when remaining factors of the denominator equals 0. So anytime you cancel a factor out from the numerator and the denominator, you're going to have a hole. And vertical asymptotes occur when whatever's left over after you cancel everything, whatever factors in the denominator equals 0, those are going to be your vertical asymptotes. So for holes, first thing you're going to have to do is make sure everything is in factored form. Okay? And if a factor cancels out from the top and the bottom, that will give you the x value of the whole in the graph. Next, you're going to plug that x value back into the equation, the simplified equation anyway, to find the y value of the whole. Okay? Now for your vertical asymptotes, everything must be in factored form as well. You always want to factor everything out if you can. It just makes solving it much, much easier. Okay? After you have it in factored form, you're going to cancel anything that you can. And if there are any factors left in the denominator, set those factors equal to 0, and that will be your vertical asymptotes. All right, and there can be multiple vertical asymptotes. And remember, you always have to write each individual vertical asymptote as x equals. Each vertical asymptote is its own line, it's its own graph. So you have to write it as x equals x equals whatever the equation is. All right. So let's go on and do some examples. I think math is always going to be better explained when you actually see examples done rather than just talking about it. I think talking about it always just makes it a lot more confusing than it actually is. So let's go ahead and look at an example. For number 1, we have y equals x minus 7 all over x squared plus 6x plus 5. So remember, the very first thing we're always going to do is we're going to factor. That's the very first thing we always do, and that's what we're going to do. The top's already factored out at x minus 7. You can't factor that down any more than that. And in the bottom, we have x squared plus 6x plus 5. Since we have a coefficient of 1 in front of the x squared, we're just going to find factors of 5 that add up to 6. And that'll be x plus 5 and x plus 1. Okay, so we factored. After we factored, we're going to cancel whatever we can cancel out. So after we factor, we cancel out similar factors from the top and the bottom. In this case, we can't cancel anything out. All the factors are different from the top and the bottom, so we don't cancel anything out. And if we don't cancel anything out, that means we have no holes. Now for our vertical asymptotes, or rather, let me finish up what we have up here. After we factor, if we cancel, we're going to look for holes. And after we look for holes, we look for vertical asymptotes. So I just want to finish up that little sequence of how you should go about this problem. So you factor first, then you cancel out similar factors. You look for holes, and then you look for vertical asymptotes. So we factored out, we can't cancel anything, so we did that. We look for holes, we don't have any holes. So last, we're going to look for vertical asymptotes, and our vertical asymptotes are going to be the factors in the denominator set equal to 0. So x plus 5 equals 0, and x plus 1 equals 0. So we set these both equal to 0 and solve for x. So x equals -5, and x equals -1. And that's exactly what our two vertical asymptotes are going to be. And remember, you have to set it as x equals -5 and x equals -1. Their equations, you have to have it as x equals. Okay? So now for our domain. Our domain is going to be all real numbers other than our x values in our vertical asymptotes and our holes. So our set notation will be every value of x such that x does not equal what our vertical asymptotes equal and what our x value of the holes are equal to. So in this case, x cannot equal -5 or -1. So -5 or -1. And we don't have any holes in this problem, so we don't have to worry about that. So our domain is every value of x such that x does not equal -5 or -1. And for our interval notation, that's going to be from -infinity to our smaller of the two x values. So -5, you put that union, -5 to the bigger of the two x values that we cannot equal, which is -1, then union -1 to infinity. And that's our interval notation of the domain. Okay? So that's number one. Let's go on to number two. Number two, remember, we're going to go about it the same way. We're going to factor first. We're going to cancel out anything we can cancel out if we can. We'll look for holes. Then we look for vertical asymptotes. So that's the sequence we're going to go about solving all these problems. So first thing we're going to do is factor. And when we factor the numerator and the denominator. It just so happens that we don't have to factor out the numerator in this problem. So we just leave it as x minus 2. For the denominator, we have x squared plus x minus 6. Our coefficient of x squared is 1. So we just need to find factors of -6 that add up to give you +1. And that'll be x plus 3 and x minus 2. 3 times 2 is -6, and 3 plus 2 is +1. That's our factored form of x squared plus x minus 6. So now that we're done factoring, we're done with this. Next thing we're going to do is we're going to see, can we cancel anything else? And we see we have the same factor here, x minus 2 on the top and x minus 2 on the bottom. So we can cancel both of these out. And when we do, we're left with, actually just rewrite it, we're left with y equals 1 all over x plus 3. Okay? So we canceled everything out, so we're done with that. And since we canceled something out, that means we're going to have a hole. We canceled out the factor x minus 2, so that means our x value of the hole will be when x minus 2 equals 0, or just x equals 2. So that's our x value of the hole. And now to find our y value of the hole, we're going to take that x value we just found and put it into our simplified equation. So we get y equals 1 all over 2 plus 3. Since that 2 is our x value of the hole, and when we solve that out, we get 1/5. So our y value of the hole is 1/5. Okay? So now that we're done with our holes, we're done with finding our holes, we can cross that out. We're going to look for our vertical asymptotes. Okay, and to find our vertical asymptotes, we're going to use our most simplified version of the equation that we have, and that's that y equals 1 all over x plus 3. So our vertical asymptote will be whenever the denominator equals 0. So in this case, when x plus 3, that's our factor of the denominator. When that equals 0 is when we have a vertical asymptote. So in this case, when x equals negative 3. So our vertical asymptote is x equals negative 3. So we have our holes, we have our vertical asymptotes. Now we need to figure out what our domain is. Our domain will be every single x value other than the x values on the vertical asymptote and in the holes. So in this case, it will be every x value such that x does not equal this negative 3 over here, and the x value of the hole over there. So it cannot equal negative 3 or 2, since our vertical asymptotes and the holes are both discontinuities in the graph, so nothing happens at those x values. So our domain is every x value other than what happens on the vertical asymptote and the x value of the hole. So our interval notation will be from negative infinity all the way to our smaller of the two x values that we cannot equal, which is negative 3, union the smaller of the two x values to the bigger one, negative 3 to 2, and then 2 to infinity. That's our interval notation of number 2. Okay? So let's go on to the last example, number 3. Let's write out our little flow chart of how to go about this. We factor, and then we cancel anything we can cancel out. We look for holes, and then we look for vertical asymptotes. Okay? So first thing we're going to do is we're going to factor everything we can out. The numerator is already factored out, so we don't have to worry about that. But the denominator needs to be factored out, so we're going to do that. And we have 2x squared minus 11x minus 6. That's our denominator. And we see our coefficient of x squared is 2. It's not 1. So that means we're going to use the x in the box method. That's the method I like to use. I think it makes the most sense. So that's what we're going to use. Okay, so the top of our x is going to be our a times our c, our negative 12, and the bottom of our x will be our b value of negative 11. So now we need to figure out what factors of negative 12 add up to give you negative 11. That will be negative 12 and positive 1. Negative 12 times 1 is negative 12. Negative 12 plus 1 is negative 11. So once we have our factors out, figured out, we're going to put them all in our box. It's not a very big box, let's redraw that. Okay, so the top left of our box is our ax squared, our 2x squared. The bottom right is our c value of negative 6, and our diagonals are the factors we just found, which is just 1x. Okay, so now we're going to find the GCF of the first row. The GCF of 2x squared and negative 12x is 2x. And now we're going to divide into it. 2x times what gives us 2x squared? That's just x. 2x times what gives us negative 12x? That's negative 6. And now x times what gives us 1x? That's just 1. And we can double check. 1 times negative 6 is negative 6. So if we multiply into this box, we get that same exact thing. So we figured out our factors of 2x squared minus 11x minus 6. That would be 2x plus 1 and x minus 6. So we're done factoring. We're going to go on and we're going to see, can we cancel anything else? All right. So we see we have a factor of x minus 6 in the top and x minus 6 in the bottom, right? That means we can cancel both of those out. And when we do, we've canceled everything we can out, and we're left with 1 all over 2x plus 1. Okay? So our new simplified equation is y equals 1 over 2x plus 1. But before we actually use that, we need to figure out what our holes are going to be, right? We factored, we canceled stuff out, and now we're going to look for holes. So we cancel out x minus 6. That means our x value of the hole will be 6, right? We're going to set the factor we canceled out equal to 0 and solve for x. X minus 6 when it's set equal to 0, you get x equals 6. That's our x value of the hole. We're going to take that 6 and plug it into our new simplified equation. So we have y equals 1 all over 2 times 6 plus 1. We solve that out. We get y equals 1 all over 12 plus 1, or just 1 over 13. So our whole is at 6, comma 1 over 13. So we found our whole. We're done looking for our wholes. All that's left now is to look for our vertical asymptotes. And remember, for our vertical asymptote, we're going to use the most simplified version of the equation that we have. And in this case, it's y equals 1 all over 2x plus 1. So we're going to set all our factors in the denominator equal to 0. The only factor in the denominator that we have is 2x plus 1. So we're going to set that equal to 0. And when we do, we get 2x equals negative 1, or just x equals negative 1/2. And that's what our vertical asymptote is equal to. It's x equals negative 1/2. So we figured out our wholes, we figured out our vertical asymptotes, so we're done with that as well. All that's left is to put in our domain. Our domain, remember, it's going to be every single real x value other than the x value of the whole and our vertical asymptotes. So in this case, our set notation will be every value of x, such that x does not equal this negative 1/2 in our vertical asymptote, and the x value of our whole, which is 6. Okay? So our set notation is x, every value of x is that x does not equal negative 1/2, which is our vertical asymptote, and 6, which is the x of the whole. Okay? Next, we're going to figure out our interval notation of the domain. Before I do that, I'm going to actually move this over here, give myself a little more room. And so my interval notation will be from negative infinity to the smaller of the two x values, which is negative 1/2, union the smaller of the two x values that we cannot equal to the bigger one, which is 6, union 6 to infinity. And that's going to be the interval notation of number 3, of the domain for number 3. All right? So that's all the examples that we have. There is a little clue card in the bottom of that page. I think it's a very good clue card, but a very simplified version of even that is just going to be my flowchart on the top. You factor it out, you cancel whatever you can cancel out, you look for holes from what you canceled out, and then you look for your vertical asymptotes. Okay? Other than that, guys, hopefully this video helps, and that's it.